Hello and welcome YouTube, Mr. Rumson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. So step on inside and let's learn a little bit about graphing quadratic equations when they are represented in vertex form. Now, I did some videos pretty recently, actually. I just did one on Halloween on transforming quadratic equations and cubic functions as well, and you know, you can use that video as an instance of what we're going to be doing here as well. I think that one talks a little bit more heavily on some other things, and of course as cubic. So this one just focused on vertex form, and another little wrinkle on vertex form, given that we are going to be converting into vertex form from standard form with some problems. Otherwise, some of this stuff is largely going to be the same from those. If you already know how to do this stuff, then this is just more practice problems, really. So, you know, you can find your own exit from there. Otherwise, stick on in with me. We're going to be doing some things together here. I don't know how much I want to teach this in the sense that you've heard it before or not, so I'll do what I can, and once I feel like I've really covered some bases, I'll go ahead and speed this up. Okay, so I have 12 practice problems, I believe, that we're going to be doing, and they are right here. And then I have these graph papers, these tall axes, and I think I got to zoom out a little bit to make them look as appreciable as possible here. So I always try and promise these things, and I can't always follow through because this uploads the next morning, but I'll try and maybe put a PDF of this graph paper here. We get 6 sets of tall axes on either side if you print them out, and you can do that. So these graphs right here, these equations, they're going to be in vertex form, what's called vertex form for the first 8, and then the last 4 are going to be in what's called standard form, where I'm going to convert them into vertex form with you. There's more than one way to do it, but we are going to be using it by what's called completing the square. And I did completing the square, solving completing the square with all of us before in the past, so hopefully we'll kind of learn how to do this here as well. Okay, so transforming quadratic functions, yeah, sort of. This is going to be just more about vertex form, guys, and the vertex form of a quadratic equation is y equals a times x minus h quantity squared plus k. Now the a value represents what is called a vertical stretch factor. I'm just going to put VSF for now. This makes it grow taller, compress to be shorter, and it flips it over as well. H and K represents the vertex values, and if you've been with me at all, you know that you have to flip that sign. As it says a minus h here, h is whatever the opposite of the thing is. If it says minus 3, then that means it's a 3. Flip the sign, and the k means you keep the sign there, the plus k, positive k. So there's kind of that instance there. Flip, keep. I think we've dealt with this stuff before. Hopefully you can understand what I'm talking about when I actually work that in. So here we go. Sketch the graph of each function. Now I'm just going to pull out information from here and do what I need to here. And then from there, I'll just go ahead and draw the graph. I'll even draw you axes of symmetry if you need those as well. I got to remember to do that, but I'll go ahead and try. All right, so number 1, y equals the quantity x plus 3 squared plus 4. Now, just for this problem here, at least for now, if I were to rewrite this in such a way that looked like vertex form right here, then there would be a 1 in front of here. This would be x minus negative 3 squared plus 4. And I'm mentioning all this so you know exactly what values, what parameters we're working with on a, h, and k. I don't see a number in front of there, so that means that the a value is 1. And what are we subtracting to make this say plus 3? We are subtracting a negative 3. That means the h value is negative 3, and of course the k value is 4. You don't have to write that, but you know, a lot of people ask, you know, why is a plus a minus now? Well, because it's all about what we were subtracting inside there. So here's what we're going to do, guys. We're going to start, here's how I want to graph them. I'm going to go completely without a table. We're going to start at the point negative 3 comma 4, the vertex. These graphs have this U shape to them, and the vertex is this bottommost point. And again, I'm doing some of this with a slight understanding that you've graphed some of these before. You've seen a parabola, and you know what it means to square a value. So a parabola has a vertex like this, a U shape, or it can be upside down, but not this one. And we're going to start at that vertex right here. Every other point from here is going to be displaced in such a way as parabolas would. When you square values, what they become. And hopefully this will make as much sense as possible because, like I said, I don't really know to what level I want to teach this stuff. I do this for my students first, I'll be honest. I do this for my students first, and if they learned it in class, then there's something to that can be said. So this is more a solution guide video for them than anything else. I did a lot of videos on this thing in the past. You can find other ones on it. So I think I'm just going to live with that. So, okay, we're going to start at negative 3 comma 4, the vertex right here. And what I'm going to do is I'm going to give this thing a U shape. Now, parabolas do not have a slope. They do not have a constant rise and run. But what I can find are specific values, these critical values here, that allow us to understand where this can go from here. Where this can go from here by knowing how quadratic functions work. For example, when I move this value over 1 like this, I will go up however much I went over squared. So if I go over 1, I'm going to go up 1 squared, which is 1. From the vertex, if I go over 2, I'm going to go up 2 squared, which is 4. I'm doing squareds because these are quadratic functions. That's what quadratic functions will do. This is number 1, by the way. If I go over 3, I'm going to go up 3 squared, which is 9. I can't fit the next one, but if I went over 4, I would go up 16, because that's 4 squared. Now, all parabolas are symmetrical, and when I say they're symmetrical, I mean that they're just like absolute value functions of which I've done on this channel. There's this axis of symmetry, this vertical line that goes through the vertex, not the y-axis in this case. It could be, but it's not. That states, going through the vertex there, that points that reflect across here, there are points that reflect across that are the same height. They are equidistant from the axis of symmetry and the same height. You don't need to draw the axis, but if it helps you get these things down and say, this is where these other points go, that negative 1 squared is 1, negative 2 squared is 4, and negative 3 squared is 9, all positives. Then you get the result that is this graph. This graph is probably, I'm not going to use the space very much all the time on these axes, the way that they're constructed and such, but I'll make sure to plot as many points as I can fit always, and maybe stretch the bounds just a little bit if I possibly can. If you ever see me peering my eyes like this, I'm peering at this game in the background. There's a 111 left on it. I don't know what's the ball anymore. But there's 111 left, and I just keep trying to see, like, did something big happen? So I apologize for that. So there's the graph right there, guys. There's the graph where we, I didn't use a table at all. Now, you can totally use a table. And my whole idea of this 1, 1, 2, 4, 3, 9 thing, guys, is I'm circumventing that. First of all, I translated the vertex first, and I put everything in relation to the vertex. That means that whole plus 3 that's inside the equation and plus 4 that's after, we've already taken care of that. All that we need to take care of now is what's being squared, and really what's going to multiply by it outside, what that a value is. And right now the a value is 1, so we don't have to pay any more attention to that outside of this whole squaring our numbers. 1, 1, 2, 4, and of course 3, 9 would take place right there. All right, let's move forward. Number 2. Y equals x plus 2 quantity squared minus 4. Very similar structure to this whole stuff here. The a value is 1, as there's no change on that. If it doesn't change, I might not mention it, and it looks like it's going to change every point here on out. So don't get used to this being 1 very often. And your vertex is going to be at, I don't know if I should put a as 1 or stretch factor is 1, but either way. There's really no stretch to the normal parent function. The vertex is at negative 2 comma negative 4. So flip that sign, keep that sign here. Negative 2, negative 4. So this time right here, guys, we're going to be going, number 2. We're going to be going 2 left and 4 down right here. And there's the first point, the vertex. This graph goes upward as the a value is still a positive 1. And that same kind of thing's going to apply. You go 1 over, you square 1. It's 1 up. You go 2 over, you square 2, which is 4. So 1, 1, 2, 4. And I'm going to plot as many points as I can fit. 3, 9. And I can fit some more here. So 4, 16. I think that's up here. No, wait, hold on. Where am I? Yeah? Wait, see, yeah, 4, 16. 5, 25 I can't really fit, but 5 squared is 25, right? Axis of symmetry, I think I made a promise, and I think I'll hold to it right now, for now. So axis of symmetry here, let's reflect points across it. You know, at some point I might not draw it, because I think at some point I want you to see if you can kind of determine it for yourself. And again, what I'm doing is I'm reflecting points across the axis. Any points that are the same height are equidistant away right there. So let's go ahead and let's do this thing. Connect the dots. Something's got to be happening in that game. Time's got to be running down. Maybe they're kneeling. I have no idea. But we got to be near the end. It's Cowboys, Vikings. Vikings are up by 3, or they were. You guys can draw while I was looking at that. Okay, here we go. So there's that. And guys, remember, it is a U shape. I know I'm not drawing the best with this thing here. My technology is limited to, what it is I can do. I just want to make sure I got the points all correct there. And we move forward. Excuse me. Number 3. Y equals negative. And there's the quantity x minus 4 squared plus 4. So the negative means that we have an a value of negative 1. Remember, I can't see the number there. But that means not being able to see the number means it's a 1, but there's still a negative. So negative 1. And your vertex is at 4, 4. This time. Now, vertex form is good where it's at, guys. Don't try and do anything by squaring this value and doing what have you. You're going to mess up, and it's not going to help you. There are things to do if we turn it into standard form, and I'll show you what at a different time when we talk about standard form, converting into standard form. But a equaling negative 1. The only thing that's going to change here, guys, is after you square a value, you multiply it by negative 1, it's going to flip over. Everything's going to reflect across the x-axis in that sort of way. It's going to flip upside down. So when I talk about 1, 1, 2, 4, 3, 9, etc., now it's going to be 1, 1, 2, 4, 3, 9. Yeah, we square the number, but we multiply it by its negative. So I'm going to start at 4, 4 here, and I'm going to change myself. Looks like they're getting near the end zone there. I don't know what's going on, though. I think they just scored. Is that Gallup? Who was that? No, Cooper. Oh, Cooper. Okay, here we go. 4, 4. Start at 4, 4. Sorry about that. Me being distracted. All right. This a is negative 1. So we're going to go 1, 1, 2, 4, 3, 9, 4, 16. It really is just an upside down version of that other graph, sort of. Different vertex, but. And that's kind of all I can fit. Let's see if we can do this without the axis of symmetry. Go across. 2 away from the axis. 3 away from the axis. 4 away from the axis of symmetry right there. So you can still count that. I just think it takes longer to count that way than just across. Really, the more you can do in understanding what parabolas do, I think the better off you are. Listen, I'm not going to say that you can't use a table, but if you use a table, if you end up being one of them table users, 2 things. Number 1, you want to find your vertex first anyway. You want to build, I'm sorry, as I keep trying to draw this. Number 1, you want to find your vertex anyway. You want to build your table around your vertex. You want to know that you don't go completely out of window range. You want to know where that symmetry is built, right? You don't want to build half a parabola and not have the other half because you stopped building a table and you didn't know where to find points. So you want your table, you want your vertex first anyway. You want your vertex to be your middle value. Number 2, you don't want to compute more in a table than you don't have. You don't want to compute more in a table than you have to. If you find the vertex and then you plot a table to get this point, this point, this point, and for some reason that point, you do all those points there. Don't calculate what these ones. Don't spend time calculating those. Do what I'm doing. Reflect across. So do as much as you can as far as understanding how quadratics work, and it'll speed up your graphability. I promise you that. Now, I'm not going to use a table. I'm going to use the concept of 1, 1, 2, 4, 3, 9, etc. And things are going to change a little bit now that we're going to do some other problems here. Let's look at number 4. Number 4, y equals 2 times x plus 4, quantity squared plus 1. So this 2 here, how's that going to change? The a value being 2, remember, it means a vertical stretch factor. This thing is going to start stretching this thing. This graph is going to get taller. Now, the vertex is at negative 4, 1. So we're going to start at negative 4, 1 on number 4. I hate when it does that. So let's start at negative 4, 1 right here. Now this thing has a stretch factor of 2. Now what that means here, so here's what I'm going to do. Don't plot my points just yet because I'm actually going to move mine. So let's consider 1, 1, 2, 4, and I don't know if we'll be able to fit it all here, but 3, 9, right? Let's consider those 3 right there. Now, these are mobile points. Okay. What I'm going to do is consider how tall these things are right now. This is 1. And remember, everything I'm doing is in relation to the vertex, guys. This is like my new origin. I'm not looking at this point as negative 3, negative 2. I'm looking at it as 1, 1. This is my vertex. So how tall is this point? It's not 2 up. It's just 1 up. It's 1 up. After you square your value to get 1, we are now going to be doubling our value. That times 2 means we're going to double it. So times 2, instead of being 1 up, it's going to be 2 up right here. This next one, instead of being 4 up, let's double that. It's going to be 8 up. This one, instead of being 9 up, it's going to be 18 up. Now, I don't think I can really fit that. It's going to be like way up here or something like that. But we double all our heights. It's not 1, 1. It's 1, 2. 1 times 2. It's not 2, 4. It's 2, 8. 4 times 2. It's not 3, 9. It's 3, 18. 9 times 2. So that's what the stretch factor does. See, last time we multiplied by -1. Remember when it flipped over? And this time, we get to double them. And what? I can reflect points across the, in this case, invisible axis of symmetry right there. And I'll even plot those points up there just because I can. Why not? I can do it. So I'm going to. These tall graphs deserve their moment in the sun. And, it's good to make moment now to talk about this. I mentioned the U shape, but also one other thing, and these graphs aren't going to do it full justice, guys. That side actually wasn't bad. But these graphs do go on forever. Obviously, there's an unlimited domain. Excuse me. Obviously, there's an unlimited range. It goes on forever. But there's also an unlimited domain. It goes forever left and right. And I know that it might kind of look weird to do that because of how sharp it gets. Remember, it's not a constant slope, right? It keeps increasing its sharpness over time and gets a lot taller. So steep to the point of almost appearing like it's near verticality, complete upright verticalness. But it never is. And one of the things I can make mention of when I plot these points, when I'm saying I can do it, is I really should, because I want you to get that idea of it still goes left. It takes a little more to get one unit over, but still goes over. Don't draw this thing vertical like this ever at any point, because you're breaking the idea of this being a function. You're breaking the idea of an all real number domain. You want to make sure that you're maintaining that. Not a great looking graph as far as my curve goes, but it should keep continuing left. It should keep continuing right. The Vikings might be cooked, guys. All right, so that's number 4 here. Number 5. Now we have a 1/2 here for number 5. Y equals 1/2 times x plus 4 quantity squared plus 2. Now these are kind of pre-generated problems. I kind of randomize till I find what I'm looking for. So you're going to find a lot of these 4s. Nothing seems to go really beyond 4 when it comes to vertex stuff, and I apologize for that. There's nothing really I can do. The a value here is going to be 1/2. And here the HK, the vertex is at -4, 2. So the A being 1/2, multiplying by 1/2 means dividing by 2. The last time we multiplied by 2, we doubled the heights. Now we're going to halve the heights. We're going to divide all the heights by 2. And listen, guys, I just want to make mention, I've done quadratic graphs on my channel forever. There are a bunch of videos where I have this. Some are bad. This might be one of the bad ones. Some are really bad or just kind of sloppy or old or whatever. -4, 2. I'm sorry. I had to look at that. And, but you'll see them anywhere. You can find some when I taught in pre-calc. You can find some before that. They're everywhere, guys. This 1, 1, 2, 4 stuff, I haven't evaded it for years. This is like my 8th year teaching. And I've had the channel for about 10 years now. So that's, even that's kind of that. Anyway, okay, so now the A value is 1/2. So let's remember how we square numbers. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. We're going to divide those heights by 2. We're going to take half of them, divide it by 2. It's not 1, 1, but 1, 1/2. Looks like the Cowboys one. It's not 2, 4, but 2, 2. That's half of 4. It's not 3, 9, but 3, 4.5. Half of 9 is 4.5. And, maybe some of those points are things that maybe you don't really know, or maybe it's not worth using the calculator. Maybe skip the odds. Maybe just go to the evens only and just talk about just, half of 4 and half of the next one, which is half of 16. Instead of 4, 16, let's go 4, 8. But again, I'm going to plot what I can fit here. 5, 25. No, half of 25 is 12.5. So that's going to be, I think, up here. Like that. Now, by the way, this is 12.5 up from here. That's at 14.5 right now on Y, but 12.5 up from 2. So those are the only ones I can fit right there. I'd love to do half of 36, which is 18. You know what? I just can't fit it. Just can't fit it. So let's just plot what we can. And this gives you kind of a more appreciable curve. This one gets you more of the U that you're like, there's that U I've been pining for. You get a lot more curve action to it, a little more gradual. I like them more. I like the 1/2 and the 1/4 a heck of a lot when it comes to graphing. I don't know if I gave you a 1/4 here. I don't know if I could randomize it to the point that I got one. Kind of hope I got one. We'll see. All right, so there's number 5. Now, this will start to speed up as we start to see more problems like what we've done, if that makes sense. Okay, number 6. y equals negative 2 times x plus 1 quantity squared plus 4. So here on number 6, the a value is negative 2. The h value is negative 1. The k value is 4. That's our vertex. Negative 1 comma 4. And this is negative 2. So negative 2 means doubling the height, but it also means flipping it over. So that means I got to get out of the way right here. So was it negative 1, 4? I forget. I'm sorry. Negative 1, 4. So number 6, the a value is negative 2. And then we got negative 1, 4 on the horizon here. So we're going to double the heights, but we're going to go downward. So not 1, 1, but 1, 2. Not 2, 4, but 2, 8. And I can definitely fit this one. Not 3, 9, but 3, 18. So that's 9. And then another 9 would be down, I think, right here. Okay. So over here, let's reflect these across. 2 away, 2 away, 3 away, 3 away, I think, right there. I don't want to have gone too far over. Okay, you know, it is easier if I have the axis of symmetry, to be honest. All right. And there we go. So I'm not as... Even though these 2's and stuff like that, even though I don't have fractions to run into, they are harder to draw. They're not as good looking of drawings as I think the other ones are. I'll be honest. All right, so those are the first 6. Now I have 6 more to go, and again, this half will be faster, even though I'm 20 minutes in. This should end kind of... Well, I take it back. We're gonna do some completing the square stuff later, so we'll see how that goes time-wise. But the graphs themselves, I think, will be a little faster. Number 7. Ooh, I got a 4. Oh man, don't have as much fun with the taller ones here. A lot of 4s all over, right? The a value is 4, and then the vertex is at, it looks like 4, negative 4. So okay, here we go with a 4 here on number 7. We're going to be at 4, negative 4 for our vertex, and it's a 4 for the stretch factor. So it's not 1, 1, but 1, 4. We're multiplying the 1 by 4. It's not 2, 4, but 2, 16. We got to go 16 up from here just to get the next set of points when we're another x value over, like that. And really, that's all I can fit. There's definitely no way that I can fit 3, 36, which would be 9 times 4. But I am going to plot what I can here and draw that curve. Super tall. And again, this is a U shape. It's just a super tall one. This doesn't V out at the end, right? These aren't straight lines. It does curve in. And it doesn't really curve outward like that, but it definitely doesn't curve straight upward either. So I think that's pretty good. And you can see how that graph was a lot faster, despite the fact that, super tall and probably not my favorite. But it's there. Number 8. Now, negative 1/2 times x minus 2 plus 4. So negative 1/2 here. We are going to flip it over, and we're going to divide those by 2. So we've kind of seen all that before, and we got a 2 for vertex. So let's see how fast we can kind of take care of this one. Was it 2, 4? I always forget. I'm focused more on the stretch factor. 2, 4. All right, 2, 4 right here, and negative 1/2. Okay, here we go. 1, 1/2, that's half of 1. 2, 2, because that's half of 4. 3, 4.5, because that's half of 9. 4, 8, because that's half of 16. 5, 12.5, because that's half of 25. I hope I'm counting that right. So basically, if you're wondering how I'm counting so fast, like, seriously, if you're wondering how I'm counting so fast, I'm not counting. I'm calculating. I don't know if you noticed this, at least with my graphs here. There are these little hashes. I'm going to draw them a little thicker right here. These little hashes right here that I have set up for every 5 increments. You can see them up here. You can see them right here as well. Okay, I don't have the numbers, but I have those increments there. That's for every 5 things. So what I'm doing, I'm not counting that. This is at 4, right? So when I said I have to go down 12.5, what's 4 minus 12.5? 4 minus 12 is negative 8, and this 4 minus 12.5 is negative 8.5. Where's negative 8.5? It's 1.5 up from negative 10. Yes, I'm doing all of that at that point, right? That's how I'm getting at really fast for you. So let's do the next one. We got to do half of, what is it? We're 6 over? Half of 36, which is 18. So what am I going to do when I count 18? I'm going to do 4 minus, wait, what did I say, 18? I'm going to do 4 minus 18, which is negative 14. You want to know where negative 14 is from here? It's 1 away from negative 15 right there. So that's where I can kind of get that fast bit going. This is one of those ones where I feel the axis of symmetry would just be nice to have. It's just going to be kind of easier for me to count over this way as well. So here we go. 1 away, 2 away, 3 away, 4 away, 5 away, 6 away. There we go. Love that kind of waterfall look that we can have there. So here we go. Woo. All right. I'm getting as many points there as I can fit. All without a table. How many points did I get without a table? 1, 2, 3, 4, 5, 6. 13 total points without a single use of a table. I can do it pretty whip fast as well, and so can you. That's why I'm giving you this. Never go straight down. All right. Love it. Okay. Now, numbers 9 through 12. There are 4 more to do, but you'll notice they're not in vertex form. In fact, they are in standard form, okay? These ones, oh my goodness, what did I just do? These ones are in standard form here. So, here's what we're going to do. I want to get in vertex form. If you notice what vertex form has, guys, it has a factored perfect square trinomial. We can get a perfect square trinomial if we do what's called completing the square. We can complete the square if we take whatever term is here, the constant, and kind of move it out of the way. We want to find another term here, another constant that makes right here a perfect square trinomial with the x squared and the negative 2x. Now, unlike us solving by completing the square before, I'm doing this all on the same side of the equation. So I'm not trying to solve for x. I'm trying to get it into the vertex form right here. So here's what's going to happen. I have y equals x squared minus 2x. And the minus 1, you know, it kind of almost is the perfect square trinomial, but it's not. I got to find a new term that's going to go here to add in. Because this is going to be the perfect square trinomial that I get to factor down. This is going to be the perfect square trinomial that I get to factor down. Now, the minus 1 is still here, right? The minus 1 is still here. Now, whatever I'm going to add here will make my equation unbalanced. I have to make sure that my equation maintains its balance ultimately when all is said and done with this. So if normally what I would do in one of these equations where I solve is whatever I add to one side, I would add to the other side. I'm not going to touch this side of the equation. I'm going to keep the y as a y. So now whatever I add to this side of the equation, I want to subtract on the same side of the equation. This keeps balance, right? This keeps balance. Now, I'm going to assume you've done completing the square with me before. You've done completing the square in general. Negative 2 divided by 2 is negative 1. And negative 1 squared is positive 1. 1 completes the square, plus 1. And so I added 1 here. Let me kind of darken this. I added 1 here, so I'm going to subtract 1 here. You know why? 1 minus 1 is 0. I have to make sure that I didn't change my equation's overall thing. What I did, though, was I made a perfect square trinomial right here. This whole thing right here can factor down into a squared quantity. What does it factor down into? X minus 1 quantity squared. X minus 1 quantity squared. Now, negative 1 minus 1 is negative 2. You know what we just did? We just created the vertex form equivalent of this quadratic equation written in standard form. Now, the next video you see of me, maybe not that I don't know if I want to do standard form or factored form yet, but the next video, one of the next videos you see of me, guys, I'm going to graph out of standard form as well. And of course, you can convert to vertex form, but I'm actually going to use standard form to graph, get the vertex, things like that. But we can take standard form, convert it into vertex form by completing the square. Obviously, there's certain terms you might want, and there's certain times you might say, maybe I wouldn't want to do this way. But this is a really good way of doing it. Grabbing the vertex, and you know what? This a value was a 1, and was a 1, and it still is a 1. Right? The a value was and still is a 1. And whatever the a value is here remains as the a value in the other ones that we're going to see. Or it can get a little dicey depending on what you do, which is why completing the square won't be everybody's favorite thing. All right, but let's go ahead and take this one and let's graph it. So the a value is 1 and the vertex is at 1, negative 2. Right? So we took this thing, got it in its vertex form. Vertex is at 1, negative 2. Let's go to work on it. Number 9 here. 1, negative 2. Okay, I don't have to move myself then. So 1, negative 2 right here, and the a value was 1. So what do we do? 1, 1, 2, 4, 3, 9, 4, 16. Again, I did negative 2 plus 16. And reflect across those points right there, across the axis of symmetry right there for all the other points. And there's the graph. I first got it into vertex form so I could use the vertex get the thing. One more time, guys. When I show you standard form, I'm going to show you a different way to get the vertex. When we do factored form, I'll show you another way to get the vertex. There are multiple ways you can get that vertex. Some will be better than others depending on the nature of the problem. Completing the square is good for the problem I just had with it being a 1x squared and the even linear coefficient, and we're about to do it again. So let's continue forward and let's look at number 10. Y equals x squared plus 8x plus 14. I'm going to do the exact same thing I did last time where I use the x squared plus 8x. Remember, it is a 1x squared. I need a 1x squared to do this, and I'm going to add something here to complete the square. Now the 14 still exists here, and whatever I add over here, I also have to subtract because I'm on the same side of the equation. Now the value that I put in here is where I take 8, divide it by 2 to get 4, and square it to get 16. So I add 16 and I subtract 16. The difference is I take what I just put here and I'm going to factor it into a perfect square trinomial. This is x plus 4 quantity squared. This is x plus 4 quantity squared, right? Just that guy right there. And then 14 minus 16 is negative 2. Okay, so here's our vertex form of this thing right here. And the vertex, of course, is at negative 4, negative 2. The a value is still 1. So let's do that same thing, and we'll go relatively faster this time. So number 10, negative 4, negative 2. The a value is 1, 1, 1, 2, 4, 3, 9, 4, 16, and reflect. So again, I'll go kind of fast with those ones. Your important strategy that you're looking at now is vertex form. You can see how fast these things can be graphed, right? I hope you got your stopwatch out. I hope you're convinced. You say, you know what? Maybe we should try that. Here's the thing. There are some people who are going to live by a table. And there are, I don't know if there are benefits to a table. I guess it depends on what the a value is. But there are merits to using a table. I did mention things you should do considering whether you use a table. But I want you to think back at when you learned slope-intercept form, y equals mx plus b, and how to graph without using a table on those ones. And I want you to ask yourself if you think it was worth it to do it without a table, or if you think you'd still be using tables to this day. I think we all know the answer to that. All right, number 11. I'm going to do the same thing on completing the square, get it in vertex form. Now the difference is, when completing the square here, I need a 1x squared. So I need to factor this 2 out, not from the 15. The 15 is going to kind of kick to the wayside, right? I don't care about the 15 here. The 2, however, needs to factor out of the x squared term and the negative 12x term. So I'm going to have x squared minus 6x in here. Remember, I need a 1x squared to complete the square here. So plus, here's where we're going to have something where we divide it by 2 and square it. So divide negative 6 by 2, we get negative 3. Square it, you get 9. Yes, you have to factor that 2 out. Now, I add 9 here. So does that mean I subtract 9 here? Sort of. Do you remember in previous completing the square videos, this isn't really just a 9. What is it? It's 2 times 9. This number is really 18, right? I have to make sure that with this 2 here, I got to multiply this 9 by 2 as well. Otherwise, I will be unbalanced because I'm adding 18 right here. So I got to subtract. Excuse me. I got to subtract 18 right here as well. I factor the 2 out so I can properly complete the square. Otherwise, I'd get a different number that doesn't register the same way because the nature of squaring values. I am going to factor that part down, but I had to make sure that whatever I subtract, I double as well. So with the 2 stayed factored out, this factors down to x minus 3 quantity squared, again, assuming you've completed the square in the past. And this is 15 minus 18, so that's negative 3. So there's the vertex form of that one. That can get a little trickier for people, right? When it comes to factoring that 2 out. And really, one of the questions is, does this number stay even when you factor out a 2? So we're not dealing with fractions. And you know what? We are going to have fractions, guys. That's one thing that can kind of make some parts of the fraction stuff be a little dicey for people. And that's where we want to find any methods that we can to do possibly something else. We'll see. All right, so right here, we have an a value of 2. And the HK, the vertex, is at 3, negative 3. So stretch factor of 2 here. We're at 3, negative 3. Let's check it out. Number 11. 3, negative 3, a value of 2, 1 doubled, 2, 4 doubled, 3, 9 doubled. What's 6 plus 9 is 15. Boom. And reflect. And reflect. And reflect. Awesome. And let's go ahead and get that graph in. And I got one more graph after this. First, we must complete its square to get in vertex form. So vertex form is great because we know what the vertex is based off that. And of course, that a value is fantastic. Good news is the a value shows up in all the different forms we're going to do. Standard form, factored form, whatever form of these. But there are a lot of things in quadratics and there means where we'll do one versus another. All right, lastly, number 12. Y equals negative x squared plus 4x minus 3. Contrary to popular belief, a negative 1 is not the same thing as 1. So when it comes to completing the square, I can't just take 4, divide it by 2, and square it. I must first factor the negative 1 out, not from the negative 3. Again, I'll keep the negative 3 to the side. I don't care about that. I care about the first two terms here. Let's factor the negative 1 out, and we're left with x squared minus 4x inside here. Now I'm going to complete the square with there, and whatever I subtract here, or excuse me, whatever I add in here, I have to subtract here, but keep in mind it's got to multiply by the same negative 1 that this all multiplies by. That might sound a little confusing. Whatever I factored out here, negative 1 would multiply by this number, so negative 1 has to multiply by this number that's going to be subtracted. Negative 4 divided by 2 is negative 2. Negative 2 squared is 4. So 4 gets added, 4 gets subtracted, times the negative. So let's factor this thing down. This is negative on the outside, and we have x minus 2 quantity squared minus a negative 1, negative 3 minus a negative 1 times 4. So negative 1 times negative 4 plus, negative 3 plus 4 is 1. So there's that equation, and we will graph it. The a value being negative 1 and the vertex being at 2, 1. So here we go. Last one. Let's start at 2, 1. Let's start at 2, 1, and we go downward. 1, 1, 2, 4, 3, 9, 4, 16, and reflect across the invisible axis of symmetry. So I hope this stuff made sense. This was vertex form only, and of course, but that a value stuff, guys, once you find that vertex, all this stuff applies. We're going to do factored form, standard form, things like that, find other ways to find that vertex, etc., or just other points. But that ought to do it for this one, y'all. This was Mr. Robinson. I want to thank you so much for watching as we just did graphs. We didn't talk about too many features or anything like that, even though I drew some axes of symmetry. But thank you so much for watching, and of course, stay tuned for more, or seek my channel and see if you can find other things on graphing quadratics, because they all pretty much look like that. All right, that'll be it. Thank you. Take care.